Hello, everybody, and welcome back to another Mr. Farney Earth Science video. Here for our geologic time unit. We finally got through rock layers, we got through fossils, we got through the basics of geologic time. Now we get into the nitty-gritty, where we're going to do what only history teachers wish they could do. In today's video, we're going to do 4.1 billion years worth of history in about, we'll say 8 minutes or less. Because this section doesn't have too much detail for us to concern ourselves about right now. If we were to make this a semester-long course, we'd spend a lot of time in the Precambrian breaking down the different larger chunks of time that make up the Precambrian Eon. But for our purposes, we're just going to do a little flyby to get the greatest hits of the Precambrian, as you will. In the next video, we'll take care of the Phanerozoic. So you want to think of the Precambrian initially as it's the building blocks, the structure, the setup of Earth that led to the rise of everything that we eventually can, look out our window and see today. The Precambrian was a very different time in Earth's history because it was the construction of Earth. It was very turbulent. It was very kind of insane conditions. And they named these older periods of time that span 90% of Earth's history, billions of years, 4.6 billion years worth of time. We named them off of either underworld Greek gods or words that mean extremely dangerous and volatile. So the Precambrian, like we said in that first video, includes the Hadean, Archean, and Proterozoic eras. This is an eon that spans 90% of Earth's history. How do we know it's that old? Well, we have zircon crystals in different types of crystal rocks that we're able to radiometrically date to be about 4.4 billion years old. So if you've ever heard the expression a diamond is forever, that is incorrect. A zircon is forever, and we know that because they have been around for 4.4 billion years. That is a long period of time. So we got to start off by talking about the formation of the crust and continents. Main idea of this kind of small section is that the molten rock of Earth's early surface formed into crust. And then once we had that crust, it eventually became continents. But we can't talk about the formation of the crust without mentioning this term right here, differentiation. This is the process in which a planet becomes zoned. That means it gets different layers. When the heavy materials and elements and minerals and things like that sink towards the center of the planet because of gravity, and the lighter materials stay near the surface. That's why our elements near the surface in the largest abundance are silicon and oxygen. You'll remember when we talked about the different types of magmas, silica played a direct role in the level of viscosity in that magma, whereas our denser elements like iron sinks towards the center of our planet. That's why we have an iron solid inner core of our planet. It's also why we have the liquid outer core, the semi-solid mantle, and then our solid thin crust because of this process of differentiation. Once we have that crust formed, now we have kind of something that we can put things onto or things around. This is where we're going to talk about how the Earth's oceans were formed, and which eventually then allowed us to develop an atmosphere that was hospitable for life to begin. So these slides start with atmosphere. We could start by talking about oceans, but let's talk about the atmosphere first. It was formed from outgassing or venting from different volcanic eruptions. When we did our volcano unit, we learned that there was a lot of different gases like sulfur dioxide, a lot of ashes that are pumped into the atmosphere, but it also kicks out water vapor, carbon dioxide, and nitrogen. These venting of the volcanoes plus bombardment of Earth's early meteorites striking the surface, kicking up more material, all led and helped to the development of our early atmosphere. This picture right here is just a picture of a volcano doing some venting of some water vapor, maybe some other gases mixed therein. Oxygen in our early atmosphere was not very abundant. It was very, very little amounts. It wasn't until the emergence of Cyanobacteria, which was our first photosynthetic organism, meaning it could do photosynthesis-like reactions like plants do today to convert light and a lot of that carbon dioxide that was in our atmosphere into oxygen and different sugars. The issue was that there was so much oxygen pumped into the atmosphere at a quick period of time that the cyanobacteria actually caused a mass extinction event to the already existing anaerobic bacteria. Anaerobic meaning without oxygen. So this cyanobacteria eventually did lead to multicellular life, like different types of fish in the Cambrian, which we'll get to in the next video, but it did do a lot of damage to the existing bacteria that was already there. This image here, just, whole bunch of rocks that we can look into for evidences of that cyanobacteria. Right here, this BIFs or banded iron formations. This is a trace fossil that we can find in different types of sedimentary rock that has kind of a rust color to it. This is an indicator of these cyanobacteria that were around the 3.5 billion years ago or so. So a little bit of trace fossil, a little bit pulling in from last section. This chart, there's only one thing I really want to point out about to it, is right here, this light gray line with the gray squares. That's our carbon dioxide or our carbon in the atmosphere. And then this black line with X squares, that's the amount of oxygen. And you'll notice from the left, it's about where the formation of the Earth is, the right being today. This is not drawn to scale, but about the same point where carbon dioxide begins to drop down in the atmosphere, the amount of oxygen began to increase. This gas concentration swap confirms that the cyanobacteria was the one pumping that O2 into the atmosphere, reducing the CO2, and we can trace that back by using those trace fossils and radiometric dating in those rocks. So it kind of combines everything we've been talking about to provide the evidence for scientists that this was indeed very likely how that early atmosphere was able to get that oxygen into it. Oceans form through similar ways. We have volcanic activity, again, water vapor released during the eruptions, it condenses, it rains, and we also had meteorite and comet impacts. Meteorites and comets frequently contain ice. When it impacts an object, the amount of energy released superheats it, that ice melts, we get water. So volcanic activity and impacting meteorites and comets led to the development of our oceans. Once we had the ocean set up, once we had the atmosphere set up, we were then able to start having an increased level of life on the early Earth. How was our early life began like that anaerobic bacteria? Well, there's three different hypotheses. One, that originated in those warm, shallow oceans, those ancient oceans. Two, they are located and generated from hydrothermal vents. Three, those asteroids and meteorites that struck the Earth were carrying some sort of organic molecules with them that led to the rise of our anaerobic and our cyanobacterias. All three of these are still being debated today. There's positive and negatives to all of them. What you need to take away from this is that there are three different hypotheses for how life began, and they're still being debated today. So Precambrian, again, just as a review, 4.5 billion years ago, 4.6, depending who you talk to, up to 570 million years ago. Our earliest organisms were bacteria. And there are a few fossils, because remember from our fossil unit, we need hard parts to make a really good fossil. That's why all we have left over from these bacteria are those trace BIF layers that we find in some rocks, because they lacked hard parts. So there are very few fossils in the traditional sense. That's why we look for those trace fossils to give us more information about what was going on in those period of time. So again, during this period of time, reviewing, oceans and atmospheres were formed, spans 90% of Earth's history. Thank you, cyanobacteria. I appreciate the oxygen. The plants appreciate the oxygen. If it wasn't for you, we wouldn't be sitting here today playing this game. So that's all I have to say about this video. In the next one, we will take on the Paleozoic, Mesozoic, and Cenozoic eras, better known as the Phanerozoic Eon. We will kind of fly through the next 500 million years, learn a little bit about dinosaurs, couple mass extinction events, and have a good time while we're talking through it. So if you have any questions for me, please go ahead, reach out. If not, have a great rest of your day, and we'll see you back next time.